Okay, next let's look at another consequence of the wave-particle duality associated with quantum mechanics, and that is the subject is the Heisenberg Uncertainty Principle. And yeah, this is, as I stated, a consequence of this wave-like nature of matter that is central to quantum mechanics. And it can be stated a lot of different ways, but here's one way, that complementary pairs of observables, such as position and momentum, cannot be determined simultaneously to arbitrary precision. Okay, and so this is one of these unsettling aspects of quantum mechanics, where there's a fairly clear break from Newtonian mechanics, and where the description of reality seems perhaps somewhat unfamiliar. Because in everyday thinking, there doesn't seem to be any limitation that once you measure position of something, that you can't determine its momentum to arbitrary precision. Nevertheless, this seems to be the case. And it is fundamentally tied up in this wave description of matter because wavelengths are related to momentum. And the shorter a wave is, the more uncertain its momentum is, but the more certain its position is, and vice versa. So, and I will demonstrate this with some sketches shortly. But let's first talk about uncertainty. So if we have uncertainty in position, we'll call that delta x. We have uncertainty in momentum, we'll call that delta p. Okay, we can also refer to it in using, say, the standard deviation symbol, sigma x, or sigma p. But more typically, and in a more sort of a less restrictive way, is to just to refer to these things is just call them delta x, delta p, and say that's the uncertainty. Okay, we're not going to give the necessarily right away the precise definition of what that uncertainty is, but it, roughly speaking, it's going to be, you know, something like standard deviation or some other measurement of sort of measurement uncertainty. And the Heisenberg Uncertainty Principle, stated mathematically in its simplest form, is that delta x times delta p, so the uncertainty in position times the uncertainty in momentum, has to be greater than or equal to h bar over 2, where h bar is h over 2 pi. A lot of times we end up running into this quantity h over 2 pi, and so there's an additional symbol that we have to get used to, and that's this h bar. And let me just say for completeness here, these are the uncertainties in position, momentum. Okay. Sorry, that's a little bit hard to read. Momentum. All right. So it turns out that physics already knew that once you have a wave, there's some uncertainty associated with it. This is known for radar, which is based on radio frequency waves. This is known for sonar that's used underwater, submarines and the like. And a wave that corresponds to, say, a pop sound or a click in RF has a lot of frequencies. And either in audio frequencies, in the case of an audible click or pop, or in radio frequencies when it comes to an RF click or pop. An infinite wave has a well-defined momentum, but is spread over all space. So how would we measure momentum? Well, we won't get into a lot of details about that, but momentum is related to the energy of a wave, and also we can think of momentum as being related to the square root of frequency. Okay, and so we can see it's related to frequency. It's related specifically to the square root of frequency. And if we have a very long wave or perhaps an infinite wave that we're just looking at a piece of it, it's going to have a lot of peaks and troughs, a lot of peaks and valleys, right? And my drawing here is a little bit uneven here, but let's just assume that the wavelength is the same all the way down this wave, or I can try drawing it a little bit better here. That's a little bit more uniform. So this is going to have a well-defined frequency. How do you define the frequency? Well, basically, you count the number of crests or troughs or the number of cycles over a certain period of time. And then the frequency is essentially the number of cycles per unit time. So it's just a ratio. And the more cycles you have, the more precisely you can specify that. However, if we look at this wave in space, it's spread out. It's all over the place. Okay, so for this case, delta P is small. Delta X is large. Whereas if we look at sort of the opposite case, let's look at a short pulse. And let's say this is along the x-axis. I've been a little bit unclear about whether or not this is a time axis or a frequency axis. Well, of course, the two are related for a traveling wave. We can either monitor how the field amplitude changes with time at a fixed point in space, or we can look at how take a snapshot of the wave at some particular moment in time and look at how it varies over space. And so in this case, we're doing that with this short pulse along the x-axis. If we think about this as light, of course, there's going to be a relationship between the time picture and the position picture. So this is a pulse along the x-axis here. And notice there's a lot of uncertainty associated with the frequency of this because you don't have, where does the cycle start and end precisely? It's not quite clear. You can define something, but then if you change the shape of the pulse just a little bit, you'll get a lot different momentum. And so, so the momentum has a lot of uncertainty. So delta P is large. Delta X is small. And you can imagine some in-between cases where you got something kind of like a wave packet where it looks a little bit like this. Here you can count a few wavelengths, and there's some uncertainty associated with position, and there's also some uncertainty associated with momentum. So this is sort of the Goldilocks case where they both have sort of moderate uncertainty. And I'd like to briefly state that this is all related to the Fourier transform properties of waves. In that you can say, if you're talking about, in the case of photons, you're talking about an electric field as a function of position and time, and you can convert that to a frequency spectrum. So there's this relationship between, say, the electric field associated with a photon as a function of position and time, and the corresponding frequency spectrum. It would be as a function of frequency, or let's say maybe equivalently, once you know frequency, you can convert to wavelength, and that's related to the Fourier transform. And let me just try to make that a little bit clearer. We can plot the electric field as a function of, say, position and time. And for this is for photons or light. That would be the electric field at a particular position, at a fixed position, propagating forward in time, or we can take a snapshot of the electric field at a particular moment in time, and at least in principle we can do that. and measure the electric field as a function of position. So both of these can be related to, once you know the electric field as a function of time or as a function of position, maybe averaged over time or at a particular moment in time, then you can convert to a frequency spectrum, plot density, essentially the number of photons or the probability that the photon will have a particular frequency as a function of frequency. So if it's fairly narrow frequency, it's going to look, or moderately narrow, it's going to look like this, and that's a spectrum. And spectrum is like something that you would see in a UV-Vis spectrum, in a UV-Vis spectrometer or an NMR spectrometer, or an FTIR spectrometer, infrared spectrometer that uses Fourier transforms to transform from an interferogram into a spectrum in the infrared range. And similarly, a nuclear magnetic resonance spectrometer typically nowadays uses Fourier transforms, and it measures the radio frequency electric field as a function of time, and then does a Fourier transform to get the NMR spectrum that has sort of signal intensity versus something kind of like frequency that's given in ppm, parts per million, relative to some standard. Okay, and that's all I have to say about Heisenberg's uncertainty principle. Next, we'll be talking about Schrödinger's equation.